Hi guys, welcome to Matsi with me, Miss Resi, your teacher for today. So today we're gonna discuss about contact forces. We already have solved problems involving forces exerted between two solid objects in contact. Now we look at contact forces in more detail. A contact force perpendicular to the contact surface that prevents solid object from passing through one another is called the normal force. Consider a book resting a horizontal table surface. The normal force due to the table must have just the right magnitude to keep the book from falling through the table. If no other vertical forces act, the normal force on the book is equal in magnitude to the book's weight because the book is in equilibrium. According to Newton's third law, two objects in contact exert equal and opposite normal forces on one another. Each pushes the other away. In our example, a downward normal force is exerted on the table by the book. In everyday language, we might say that the table feels the book's weight. That is not an accurate statement. In the language of physics, the table cannot feel the gravitational force on the book. The table can only feel forces exerted on the table. What the table does feel is a normal force, a contact force, exerted on the table by the book. If the table's surface is horizontal, the normal force on the book will be vertical and equal in magnitude to the book's weight. If the surface of the table is not horizontal, the normal force is not vertical and is not equal in magnitude to the weight of the book. Remember that the normal force is perpendicular to the contact surface. Even on horizontal surface, if there are other vertical forces acting on the book, then the normal force is not equal to the magnitude to the book's weight. Never assume anything about the magnitude of the normal force. In general, we can figure out what the magnitude of the normal force must be in various situations if we have enough information about other forces. What causes normal forces? How does the table know how hard to push on the book? First, imagine putting the book on a bathroom scale instead of the table. A spring inside the scale provides the upward force. The spring knows how hard to push because it is compressed. The force it exerts increases. When the book reaches the equilibrium, the spring is exerting just the right amount of force, so there is no tendency to compress it further. The spring is compressed until it pushes up with a force equal to the book's weight. If the spring were stiffer, it would exert same upward force but with less compression. The forces that bind atoms together in a rigid solid like the table act like extremely stiff springs that can provide large forces with little compression, so little that it's usually not noticed. The book makes a tiny indentation in the surface of the table. A heavier book would make a slightly larger indentation. If the book were to be placed on a soft foam surface, the indentation would be much more noticeable. Friction, a contact force parallel to the contact surface, is called friction. We distinguish two types, static friction and kinetic or sliding friction. When the two objects are slipping or sliding across one another, as when a loose shingle slides down a roof, the friction is kinetic. When no slipping or sliding occurs, such as between the tires of a car parked on a hill and the road surface, the friction is called static. Static friction acts to prevent objects from starting to slide. Kinetic friction acts to try to make sliding object stop sliding. The two objects in contact with one another that moves with the same velocity exert static frictional forces on one another because there is no relative motion between the two. For example, if a conveyor belt carries an air freight package up an incline and the package is not sliding, the two move with the same velocity and the friction is static. Static friction. Frictional forces are complicated on the microscopic level and are an active field of current research. Despite the complexities, we can make some approximate statements about the frictional forces between dry, solid surfaces. In a simplified model, the maximum magnitude of the force of static friction that can occur in a particular situation is proportional to the magnitude of the normal force acting between the two surfaces. If you want better traction between the tires of a rear-wheel drive car and the road, it helps to put something heavy in the trunk to increase the normal force between the tires and the road. Kinetic or sliding friction. For sliding or kinetic friction, the force of the friction is only weakly dependent on the speed and is roughly proportional to the normal force. In the simplified model, we will use the force of kinetic friction is assumed to be proportional to the normal force and independent of speed. The coefficient of static friction is always larger than the coefficient of the kinetic friction for an object on a given surface. On a horizontal surface, a larger force is required to start the object moving than is required to keep it moving at a constant velocity. Direction of frictional forces. Remember that the frictional force is perpendicular to the normal force between the same two surfaces. Friction is always parallel to the contact surface, but there are many directions parallel to a given contact surface. Here are some rules for determining the direction of frictional force. Number 1. The static frictional force acts in whatever direction necessary to prevent the objects from beginning to slide or slip relatively to each other. Number 2. Kinetic friction acts in a direction that tends to make the sliding or slipping stop. If a book slides to the left along a table, the table exerts a kinetic frictional force on the book to the right, in the direction opposite to the motion of the book. Number 3. From Newton's third law, frictional force come in interaction pairs. If the table exerts a frictional force on a sliding book to the right, the book exerts a frictional force on the table to the left with the same magnitude. These bands are formed by microscopic electromagnetic forces that hold the atoms or molecules together. If the two objects are pushed together harder, the surface deforms a little more, enabling more high points to bond. That is why the force of kinetic friction and the maximum force of static friction are proportional to the normal force. A bit of lubricant drastically decreases the frictional forces because the two surfaces can float past one another without many of the high points coming into contact. In static friction, when these molecular bonds are stretched, they pull back harder. The bonds have to be broken before sliding can begin. Once sliding begins, molecular bonds are continually made and broken as high points come together in a hit or miss fashion. These bonds are generally not as strong as those formed in the absence of sliding For dry solid surfaces, the amount of friction depends on how smooth the surfaces are and how many contaminants are present on the surface. Thus, polishing two steel surfaces decrease the frictional force when they slide across each other? Not necessarily. In an extreme case, if the surfaces are extremely smooth and all surface contaminants are removed, the steel surfaces form a cold weld, essentially. They become one piece of steel. The atoms bond as strongly with their new neighbors as they do with the old. Application: equilibrium on an inclined plane. Suppose we wish to pull a large box up a frictionless incline to a loading dock platform. The three forces acting on the box represents the applied force with which we pull. The force is parallel to the incline. If we choose the x and y axes to the horizontal and vertical respectively, then two of the three forces have both x and y components. On the other hand, if we choose the x-axis parallel to the incline and the y-axis perpendicular to it, then only one of the three forces has both x and y components. On an incline, the normal force is not equal in magnitude to the weight, and it does not point straight up. Tension. Consider a heavy chandelier hanging by a chain from the ceiling. The chandelier is in equilibrium, so the upward force on it due to the chain is equal in magnitude to the chandelier's weight. With what force does the chain pull downward on the ceiling? The ceiling has to pull up with the force equal to the total weight of the chain and the chandelier. The interaction partner of this force, the force the chain exerts on the ceiling, is equal in magnitude and opposite direction. Therefore, if the weight of the chain is negligibly small compared to the weight of the chandelier, then the chain exerts forces of equal magnitude at its two ends. The forces at the ends would not be equal, however, if you grab the chain in the middle and pulled it up or down, or if we could not neglect the weight of the chain. We can generalize this observation. An ideal cord or rope, string, tendon, cable, or chain pulls in the direction of the cord with forces of equal magnitude on the objects attached to its ends as long as no external force is exerted on it anywhere between the ends. An ideal cord has zero mass and zero weight. A single link of the chain is pulled at both ends by neighboring links. The magnitude of these forces is called the tension in the chain. Similarly, a little segment of a cord is pulled at both its ends by the tension in the neighboring pieces of the cord. If the segment is in equilibrium, then the net force acting on it is zero. As long as there are no other forces exerted on the segment, the forces exerted by its neighbors must be equal in magnitude and opposite in direction. Therefore, the tension has the same value everywhere and is equal to the force that the cord exerts on the objects attached to its end.